exchange of now I pass on the word to Michelle.
Okay. Thank you. This is joint work with Joseph Chang, who was my advisor at Yale, and now I'm at Tulane, and New Orleans is not still underwater, as many people seem to think. And I'm going to talk about an asymptotic result dealing with the performance of neighbor joining. So we've heard a bit about neighbor joining already, and luckily I don't have to cover it all again, but there are some reasons why neighbor joining is interesting to study. It has some nice properties. One of those, as we've already heard, is that it's consistent. So as sequence lengths increase, it will construct the correct tree. It's computationally efficient, as Tandy pointed out, it's polynomial time. And it also has a good track record of working quite well in simulation. And this quotation may be familiar to a few people in the audience, but sort of a ringing endorsement of neighbor joining as a good baseline, as a place to start with studying methods. So any new method should be abandoned if it does not offer an advantage over NJ. So let's just review quickly how the neighbor joining algorithm actually works. So if we have a set of pairwise distances, Dij, these are the true distances or estimates, what we're doing here is we're selecting the pair of sequences that minimizes, or the distance that minimizes this criterion. So we have the distance Dij itself, and then we subtract off the average of all of the distances from I to k and from j to k. So it's really making use of all of the information related to the pairs here. We take that best pair, we define a new node k, and we set distances for all of the remaining nodes dkm. And we also set distances for dik and djk. And then in the next stage, we pull out I and j, k is its stand-in, and then we take it from there. So once information is used from I and k, we never really revisit those sequences again. And we update everything else. And we just keep going, and it iterates through until we have two left, and we join them. So what's important about this is this capital Dij. I will be making use of this in what follows, the neighbor joining criterion. And we also had some nice convergence efficiency type results for NJ. Kevin Addison in 1999 offered the following bound. And under the Cavendish-Ferris model, which is just the two-state version of the Jukes-Cantor, we assume independence, constant rate of evolution, 0 to 1 is just as likely as 1 to 0. We let capital E be the set of edges in a tree T, and we let D sub E be the length of any edge E. And we define epsilon to be the minimum edge, half the length of the minimum edge. Then NJ will recover the true tree topology with high probability if our sequence lengths k are this long. And what's important here, what's big here, is obviously this last term, the exponent of the max for Dij. So this is basically saying it will be exponential in the length of the longest pairwise distance, not the longest edge. So the interpretation then is if our sequences are exponential in the length of the longest pairwise distance, we will be successful. So that's a nice thing to know. It's nice to know that you have some convergence rate, but as has been pointed out, it would be better not to have to worry about exponential convergence. The definition of fast convergence is as follows. We would need accurate reconstruction with high probability from sequences that are only polynomial in the number of leaves that we consider. All right. So when we've heard about fast convergence a few times today, this is the formal definition. And so the question was, is neighbor joining fast converging? Can we beat the bound that Addison came up with and demonstrate that neighbor joining is in fact able to successfully reconstruct any tree from sequences of polynomial length? So this is a caterpillar. This is what they look like. They little fuzzy guys, and they have a long spine and lots of tiny little feet. All right. So we can think about a caterpillar tree as the very bland version of this, right? So we basically have a long spine or a long single edge, well, long collection of edges, and then each taxa has a little foot off of the caterpillar. All right. So each of these little edges is D sub B here, and we can have any number of taxa. And for our purposes, we're going to cripple our caterpillar, cut all his legs off, and just consider a long segment here with a bunch of nodes on it. So we're referring to this as a legless caterpillar, and we're fixing it so that every edge between each pair of nodes here is of equal. Whoa, that wasn't meant to happen. So we can go back. Okay. Whoa, wrong way. Everything's going backwards. Okay, there we go. Oh yes, I'm American. It's left to go forward here. That was a monarch. That was a monarch, as a matter of fact. It was simply the first picture that popped up on Google when I said picture of a caterpillar. All right, so why are we interested in this tree? Well, there's a few reasons, but one of them is that you can clearly see that our longest pairwise distance here will be the entire length of the spine. So this is a tough case, right? This would make Addison's bound require exponentially long sequences. So we were interested in seeing how it would do on this. And there's another reason why the caterpillar is a nice case study. It's because it can only work one way. Reconstructing a caterpillar by neighbor joining means that you basically have to work your way in from the outside. The only neighbors when you start are 1 and 2 or n minus 1 and n, because every other pair is connected by 2 nodes. So in the figure here, I don't trust myself with that stick, but what we're doing on the top left is we can either join 1 and 2 and 3 and 4 and then connect them. Or we could say join 1 and 2, join 1 and 2 to an internal node, and then add 3 and 4 there with 3. So then by symmetry, you could start with 3 and 4 and do the exact same thing. But there are only 4 ways to reconstruct a 4-leaf caterpillar tree, starting with one of the 2 neighboring pairs. And you can imagine by extension, if we make the caterpillar longer, you're just going to have more steps in between. So what this means is that we have a pretty nice way of assessing whether or not we're going to get it right. So as we've just said, the neighbor joining criterion must be minimized by one of these 2 end pairs, either 1 and 2 or n minus 1 and n. So what happens then if we consider another pair somewhere further along into the tree? And we're actually going to let this, we're going to call it G sub n because it's going to be something asymptotically that shifts with n. But we can have sequence S G sub n and S G sub n plus 1 somewhere along the tree. And we're going to define Gn to be n to the gamma for some gamma between 0 and 1/2. So you can think of this as root n. You can think of it as n to the 1/10, however you like. It's somewhere shifted. And we like it to be far enough along that basically 1 and 2 and Gn plus 1 are essentially independent, although they'll never be entirely so. The motivation for picking a sequence like this is when we first started working on this problem, we weren't sure how it was going to go, so I started looking at some simulations. And I saw that when neighbor joining made a mistake, it didn't make a mistake near 1 and 2 or n minus 1 and n. It made a mistake by kind of joining a pair right in the middle somewhere, far away from either of the ends. So we thought that this might be an interesting construction to look at. What's happening if we move far enough away from the ends that we are close to being independent from the 2 corners. And we're going to define this variable, which essentially represents the difference in the neighbor joining criterion between the criterion for our pair Gn and Gn plus 1 and for the pair 1, 2. By symmetry, you don't need to worry about n minus 1 and n. Results will be the same. So what should happen here is that this is positive, right? This should be larger. And this isn't obviously going to be a sufficient condition for fast convergence, but it would certainly be necessary, right? So if we find that this is not true, then we're done. So what we're looking for then is the behavior of this variable to see whether or not the probability that this thing is positive is in fact converging to 1, or is it doing something different. But immediately you run into a little bit of a complication here, which is the way distances are defined under these models. As you may probably know, the formal definition here, we use this logarithmic transformation on p hat ij, which is just the proportion of differences observed between the two sequences. Unfortunately, this thing is undefined whenever we have a p hat of 1/2 or greater. And in our case, these pij's are going to get pretty big. This is what it works out to. We have a j minus I in the exponent. So if our sequences are of only polynomial length, the probability that we get some distance estimates, undefined distance estimates, or proportions that are close to 1/2 or greater than 1/2 basically goes to 1/2. So we're equally likely to have things undefined or not if the i's and j's are sufficiently distant. So, well, you can stop right there and say, well, it can't be fast converging because you're going to have some undefined distances and we can't do anything with those. Well, that's kind of a wimpy way to get out of this problem. So we said, well, let's allow for the next phase, which would be a common thing that's done, is the correction of these undefined distances. So you could use any correction factor. It won't really affect our results here. But to be conservative, we said we'll set any corrected distance to be the maximum possible that it could be for sequences of length n. This is based on an even sequence length, but you have a tiny, tiny wrinkle if it's an odd sequence length. All right, so any distance that's undefined, we're just going to say it's as big as it could be for the sequence length that we see. Again, that's not really, our results aren't really dependent on that, but think about it that way for now. All right, so we're going to do that. And it's pretty difficult, obviously, to try to understand the exact probability distribution of our random variable. So instead, we focused on deriving two inequalities. We analyzed the expectation of this random variable, and then we analyzed its variance. And what we were looking for was an asymptotic upper bound for the expectation and an asymptotic lower bound for the variance. And then, by doing that, we can look at what we call the signal-to-noise ratio here, not what we call, what anyone calls, the ratio of the expectation to the standard deviation, and see how this thing behaves. All right. So here things get a little technical, well, for a while, but if we let d hat I star simply be the sum of all of the pairwise distances from from I to all the other sequences k, and we're going to let L sub n, our sequence length, be n to the s, so our polynomial sequence length. Then formally, the difference dn, if we just plug in, did it again, the neighbor joining criterion here, the first line is simply the difference between the two criteria, and then that first term there, the expectation of that first bit is just 0. Right? Because gn plus 1, gn to gn plus 1, and 1 to 2 have the exact same length, de. So that part goes to 0, and then we're left with everything else there. And we just regrouped it. So we have the difference between 1 and gn, and all the differences between 2 and gn plus 1, which are just shifted over by 1. Now, to analyze this thing, we're going to subdivide the summations into 3 regions. The first region, we're going to consider all of the positions up to gn plus 1. The second region, we're going to consider all of the positions between gn plus 2 and gn plus bn, where we let bn be some region of length n to the beta. And again, you have flexibility here. You can define beta however you like, as long as it's less than 1/2. And region 3 will be all of the stuff even past that. All right, so why did we do it this way? Well, because we get different results for each region. In region 1, by symmetry, everything cancels out. So we're done. Basically, these are all the distances from 1 to gn and points in between, and all the distances from gn to 1 and all points in between. So by symmetry, everything goes away. We don't have to worry about that region anymore. In region 2, this is a region where we've moved far enough that distances from 1 to k are quite large, but distances from gn to k are still fairly short. So these are points that are close to gn, but pretty far from 1. here, we said, all right, let's be generous. We'll say that every single distance from 1 to k is as big as it could possibly be, and all the distances from gn to k are small, and we'll just call it 2bn d star. So d star was that maximum possible distance for sequences of length n to the s. Bn was our defined length of the region. We have 2 terms. So we're being very, very conservative here. We're saying let's give the expectation the maximum value it could take. Then, as we go to region 3, now we're looking at a region where the positions are far from both gn and from 1. In here, everything is fairly close. All the distances are very close to each other. All of them are quite large. And actually, there's very, very little difference in this region for sequences of polynomial length. So this term essentially says that we basically have something which is pretty negligible when we go out this far, due to the fact that for polynomial length sequences, our estimates for gnk are not any better than our estimates for 1k, effectively. So aggregating all of that, this is the bound we end up with. Basically, we get something which is largely due to that conservative expectation that we gave for that region 2, plus something that's little o of 1 over n. All right. So those are our results for the expectation. Now we move on to the variance, which is a lot of stuff, and I'm not going to worry too much about the details here, but the main results that we went into were that we could ignore some terms. These are variances of sums, lots of covariances, pages and pages and pages of stuff here. So very quickly, we make use of a few results. The fact that all the covariance terms for pairwise results will be positive. We go through all this, and we end up, after lots of calculations, with a bound that looks like this, which basically, again, depends on gamma and beta. And finally, we end up with the following signal-to-noise ratio. So aggregating our results, if we take the ratio, we end up with the final expression you see on the bottom, which is dominated by this term n to the 1/2 minus beta. So what does that mean? Basically, it means that the limit of this ratio will approach 0. And that means that you're just as likely to be right or wrong in this case. All right, and with a few mild conditions on the distribution tail results, you end up with a probability of 1/2 of getting the right or wrong answer here. So just to close, I just wanted to mention, so what this tells us is that if we allow for any possible type of tree, we cannot improve the exponential bound. The caterpillar is a counterexample, which suffices to show that you cannot guarantee polynomial results. However, whoever deals with a caterpillar tree, there are obviously much better cases where NJ would probably perform well. And really what we need to think about is why this is happening. The problem is that we can't estimate distance as well under these conditions. And an algorithm like NJ, which needs all of the distance information, is more likely to have problems here than some others. There's a lot of math I didn't obviously put up here, but our paper is there. I have a few copies if anyone wants to look. And I'll stop. Thank you.
Any questions?
I mean, if you would use Fendi's discovering method for this particular example,
It would probably work very well.
Can you compute exactly how great the improvement
Well, you
is?
can compute, all the quartets should be quite easy to do, and then you just need to aggregate them up. So this was an example that we were thinking actually would be a very good case. Discovering would be, this is sort of the poster case for discovering,
So
right?
You will do it sometime.
Huh?
You will do it sometime.
Oh, I don't think you need to. I think it's pretty obvious. But yeah, I think these are cases where it would work quite nicely. Yeah, when you have a bunch of fixed edge lengths like that and everything can be easily merged. Yeah, I think that's right. Okay.
Questions?